As I mentioned in the introduction, a couple years ago, it was probably common to have maybe a desktop in the house, possibly a printer, your router, and nowadays it's technology's become much more ubiquitous. You can think of the speakers that we have. I have an Echo Dot that I just recently got. I've got a tablet, I've got a Wi-Fi printer, and just a number of other devices. So as the number of devices grows in the Internet of Things, we actually begin to run into a few issues. And so one of those issues are, if you think about the need to uniquely identify each device on the network, we're going to run out of IP addresses and maybe even MAC addresses, which is something people don't tend to think about. So in IPv4, right, there's 4 octets, there's 32 bits, so there are 2 to the 32 possible IP addresses, with some of them being reserved for different things like private addressing. But there's about 4 billion IPs, and we are definitely running out. The good news is, though, that IPv6 allows for more IP addresses than there are, I feel like, atoms in the universe. So 3.4 times 10 to the 38 IP addresses, which is much more than IPv4 space allows. So it's generally believed that IPv6 will provide us with enough IP addresses that IP address space is no longer an issue. Now MAC addresses are slightly different. MAC address is a 48-bit unique identifier, as you'll see here, and it's broken up into two 3-byte sections. So in the front you have the OUI, which is the organizationally unique identifier. Okay, you can see some of the bits signify different things within that first byte there. But the OUI is basically an identifier that's unique and identifies the organization who manufactured the device. So if you do come across a MAC address and you want to know what kind of device it is, you can punch those first 3 bytes into a website and it will map the OUI to the manufacturer for you. The second 3 bytes, the last 3 bytes, are actually called the universally administered address, and they just identify within that organization. So given the device with that OUI in the first 3 bytes, it's a way to identify that specific device within that organization. So you can definitely read more about it. I wanted to throw a link up there for you. So the problem is, though, that similar to IP addresses, as we put more and more devices onto the Internet of Things, we're also at risk of running out of MAC addresses. So the solution to this was not to increase the MAC address space, because it is fairly large, but it's to fix a problem in the way that the MAC addresses were given out. The way that it used to work, the IEEE, when someone, say Samsung or Apple for their iPhone, they would purchase a block of MAC addresses, and the size of the address block that was given out was the same for Samsung and Apple or Google as it is for small companies. So obviously small companies don't need a 16 million block of MAC addresses. So now what they've basically done is, if you think of the way that IP networks are subnetted, they've done that for MAC addresses, and they're only giving out a specific size portion based on your need. So if you go to the IEEE and ask for a 16 million MAC address block, they're going to need you to prove that you have a business case that supports it. Certainly for places like Samsung or Apple, that's easy to do, but for smaller organizations now, without a demonstrable need, you're going to get the smaller blocks. So they're doing that to try to conserve MAC address space here. So another big issue, obviously, is the rate of data that's generated by the Internet of Things. A pretty neat statistic if you look in the left. I think today there are something like about 11 or 12 billion devices that are connected to the so-called Internet of Things. And it's projected by the end of the decade, it's actually going to grow to 50 billion devices. And this has a lot of nice, there are a lot of nice byproducts of this. So one thing is that it's expected that the United States will surpass China in manufacturing due to all these devices, which is kind of neat. It's really basically they're saying it's the third industrial revolution, so it's quite impactful. But one of the byproducts of this is that so much data is being generated, and now it's being generated in places it was never generated before. Like I said, there are smart homes, there are smart farms, and a lot of governments are even looking to enable smart cities. So the data is distributed, there is a lot of it, and while it gives us new insights and we can access that data from anywhere, there are some other things we're going to have to think about, like how do we protect that data when it's at rest, how we protect the data when we go to retrieve it, who else can get to our data since it's probably geographically distributed. So some of these data privacy and data storage issues are things we're going to talk about as we go into our security section. Another big issue here is the bandwidth necessary to be able to sustain an internet full of things where everything's capable of transmitting or reading data over a network. So as more and more devices are connected, as you know, whether they connect wirelessly or whether they're connected to a physical network, at some point those bits right now are going to have to traverse some kind of physical medium. So even if you're connected to a Wi-Fi access point, right, that data is eventually going to go over some WAN, some LAN, some hardwired network. So with the influx in devices, we have to make sure that the networks are capable of sending the traffic efficiently so that we don't overwhelm the existing infrastructure. So kind of a neat graphic on the bandwidth demand growth on the left there. Some of those numbers were pretty staggering to me, that's how much we pass every 60 seconds. About 300 hours of YouTube videos uploaded every minute. That's just an inordinate amount. So just to give you some perspective there. But in order to cope with this, there's a number of protocols, a number of transport technologies that have come into existence to make the Internet of Things type of traffic more efficient. So if you look at the list, there's a very, very long list. You're probably familiar with a few of these. I'm sure you've heard of Bluetooth. GSM is basically LTE, so it's a 4G network. I'm sure you're probably familiar with Wi-Fi too, wireless fidelity. So that's the RF wireless signals that are in your home and in airports and things like that. But then you see a lot of low pan or LP options here. And what these are low power network protocols or physical protocols for transferring bits. And they're designed to address sort of the IoT use case where you're going to broadcast either very small distances, medium range distances, or possibly large distances, but you're probably going to be bursty in nature, right? It's not constantly transmitting. And so not only is it bursty in nature, but those bursts are usually only contain a small amount of data. So these are protocols that were optimized specifically for transmission over different lengths, like I said, really long distances, medium distances, and short distances. And they are optimized for sending basically small amounts of data, so using as little bandwidth as possible over those links. So you're going to have a homework assignment where you're going to get a chance to drill down and see some of the specific differences. They're very subtle, but I think it'll make more sense when you see the assignment.